This is actually my second UKNOF. The first one I had to attend remotely a couple years ago because we had a volcano that screwed up all the travel plans, so thanks for having me back. I want to start out with just a little bit of historical reference. It's actually, Ethernet is turning 40 years old, and the organizers have asked me not to sing. But maybe we can this afternoon at the bar or something. So interesting, yeah, Ethernet is 40 years old, and the quote I have up there in the red box is something that Bob Metcalf wrote in a memo on May 22nd, which is kind of considered the official birthday of Ethernet. He had a sketch that he drew almost a year before, and 41 years later, it turns out he was kind of right in some ways about how networks would evolve and how the signaling would work. It's not Ethernet everywhere as he drew in the picture, but you know, it is IP and Ethernet on a lot of the links, so I think that's kind of interesting that he drew that picture over 40 years ago. So I'll talk to you a little bit about what's going on with 100 gig Ethernet and then where Ethernet is going after that. So that's the what's new and what's next part of it. Alright, some of you have seen this slide before. This is probably the only old picture that I have in here, so there are a lot of new things in here for you, those who have seen me talk before. So the standard was actually approved in 2010. It's coming up on 3 years old, so by anyone's reckoning, it's a mature standard. We have a lot of media, routers, test equipment, switches that has shipped and is starting to ship now. I think it's a mature interoperable technology, broad vendor support. I think pretty much all the switch and router and optical vendors have a 100 gig solution on the market today. And we've already started second generation projects for both 40 and 100 gig that we'll see in the market next year, well, end of this year and then throughout the next couple of years. If you look at the adoption timelines, this is an interesting picture from a book called Crossing the Chasm. It's about a technology adoption life cycle and timelines, and it turns out it's a bell curve. So kind of what I remember from my statistics class is everything at the end of the day is a bell curve, as are technology adoption timelines. The interesting thing about this is that it applies to any technology. So this could be the iPhone or, I don't know, ripe Atlas probes or whatever. So it generally starts out with some innovators and early adopters doing something, and then it transitions to more of a majority technology, and then the laggards adapt sort of towards the end. Now this is not a volume graph. This is purely a timeline graph. The volume is always increasing. You know, we want to see the hockey stick effect where everything is up and to the right. So volume is totally different than adoption timelines. So if you look at where we've come, at first it was the innovators, the early adopters, and we had the first generation where we had 1 or 2 port cards and it was really, really expensive, and then we had some iterations and some cost benefits and some economies of scale and things like that, so that made it a little more affordable, got a little more density. Now we're kind of, I think, at the point we call crossing the chasm, where we're adopting into mass adoption. So that's going to be this year as several router vendors go to a form factor called the CFP2, and I'll tell you about that some more, and we get much higher density. And then over the next several years, and probably way past 2020 or into even 2022, we'll see high density. And by high density, we mean 24 to 48 port switches that are 100 gig. So there's kind of this progression. If you look at how switches have evolved, see, I remember back in 1998, we had a 24-port 100 meg with 2 gig uplink, right? And then that kind of went to, we always had this sort of 48 plus 2 or 48 plus 4 type form factor. Or now we have 48 10 gig and maybe 2 40 gigs or 4 40 gigs uplink. So I think eventually we'll see a 48-port 100 gig with, terabit uplink or something like that. But we seem to always follow this kind of progression. So kind of at this point, I wanted to ask, just by show of hands, who has already deployed 100 gig or is planning to or is in the midst of a deployment? So actually...
Well, who's deployed it?
Okay, so that's probably 10 to 12 people. And then who thinks that you'll probably deploy it maybe next year or 2015 or sometime in the future, by show of hands? Okay. So yeah, so I think the other point is that the cost will go down as the density improves. So yeah, I think we're kind of in the early majority, maybe still early adopters, but anyway, we're somewhere around the chasm, and that's kind of the key point into getting a technology into mass adoption. So a little bit about the CFP modules. You've probably seen this slide before, but basically the point is that the CFP module that we have for first generation 100 gig is rather large. It's larger than an iPhone 4. It's complex. It has a lot of components in it, and it's a kind of like, I don't know if any of you had the first generation of 10 gig. Do you remember that? It was a fixed 300 pin MSA. The optic was about this big, and it was fixed on a board, and it had these fiber jump cables that went around to the front of the line card. So this is kind of where we are with 100 gig today. This would be, you know, the cousin for the 300 pin MSA module. And then we have this other thing called the 10 by 10 MSA. So this is an alternative standard to the IEEE. If you look at the IEEE standards, there's a gap because we have a short reach multi-mode interface, which goes up to 100 meters on OM4, and we have a 10-kilometer reach. So there's no 2-kilometer intermediate sort of, you know, warehouse scale or large campus reach. So the upshot is that LR4 is really expensive if you're just going a couple of kilometers. The 10 by 10 MSA was designed to provide an alternative standard that has a shorter reach and also a lower cost, and that's because it uses a different signaling technology than the IEEE standard that's much more affordable using today's technology. Now, the interesting thing that I like to point out is that in the IEEE and in the optics world, we typically don't see a lot of network operators. It's typically a bunch of component vendors and ASIC vendors sitting around defining a standard. The difference that we had with this 10 by 10 MSA is that we had 3 network operators, which was the AMZICs, Google, and Facebook, who actually came to the meetings and participated in defining Ethernet standards. So that was really good to see. In the future, we would love it if more network operators became involved, because then we get that kind of feedback directly from you, and we don't have this encapsulation and decapsulation of information. You know, kind of like that guy in Office Space whose job is to talk to the engineers. Well, the U.S. movie Office Space. Sorry, not the British TV show. But he basically talks to the engineers, and then he talks to the customers. Right? So please, you know, come to these standards meetings yourselves, and that way we don't have to do that for you. All right, if you put it all together, this is the optics market today. And the last line, hopefully you can read it, is the relative developed recently, in particular at the beginning of the year for most of the vendors out there, is that we finally have the 100G base SR10 module. So that's the module on the very left. It's the short reach module, which is now finally available. I think that's going to make 100 gig a lot more affordable because it's a much cheaper module, as you can see by the relative price. And as I mentioned, it's finally now supported broadly by a bunch of different vendors, so you should have no trouble getting that module from whatever vendor you're using. The primary focus around 100 gig at first was the 10-kilometer optic, because that's what most people needed first. So that's why the development of some other modules like the 40-kilometer and the 100-meter-kilometer has just lagged a little bit, because it's basically the same group of people doing the technology. They can't do things in parallel. It's a lot like having a baby. You know, no matter how many people you put on this project, it's going to take 9 months. Kind of how it is with optics. So the current state of the industry is that we have a fundamental technology constraint, which is basically that we have some speed limits within the optics that are 10 gig and 25 gig. So we have a 10 by 10 electrical signaling that goes into the optic, and then we have either 10 gig signaling on the fiber or 5 gig signaling on the fiber, which depends on the type of standard that you're using. So this, as I said before, makes the module really large, also really complex, takes a lot of power, and of course complexity drives costs. So it's going to be more expensive. What we would like to do is this. We want to take all the 10 gig stuff that we have going into the module and go straight to 25 gig. So that's basically the entire difference between first and second generation technology. Is first generation is 10 by 10, second generation is 4 by 25. And this was a pretty fundamental change in electrical signaling and a technology advance that we had to make in order to do the second generation. If you look at where the module evolution is going, we had 2 first generation modules, the CFP that I showed you. There's another one that only one vendor uses as far as I know, called the CXP. You probably haven't heard of that one that much. It's really small, but the problem is that it can only support the multi-mode interfaces, so you can't use it for anything beyond 150 meters. For second generation, we unfortunately have a split in the industry. We have a standard path, and then Cisco has taken a proprietary path with their lightwave technology that they acquired. So I think that's unfortunate for the market, but you know, Cisco is allowed to do whatever they want to do. So the CFP2 module is the new industry standard module that we have. It's going to allow us to get a lot more density than we have with the CFP. As you can see, I put in front panel capacity. This just means basically how many optics could you fit onto the front panel. Not necessarily that we have the ASICs behind the optics to actually drive that much capacity. It's just, you know, how many can we fit on the front panel. So you'll see that this will almost double the density that we have. Then we have a good roadmap with more second generation components called the CFP4, which we expect sometime around 2015, and then also the QSFP28. The QSFP28 is actually in use today for 40 gig in I think some fiber channel standards, so it's not an optic specific to Ethernet. The unfortunate thing about the QSFP28, like the CXP, is that it's for multi-mode only. So we'll have a couple differences in optics technology depending on if you're using multi-mode or single mode for longer reaches. And I think that's okay. We see a lot of data center switches that just need top of rack or end of row connectivity or things like that. Here's just some different pictures that show you the relative size of the different modules. So we see CFP2 is about half the size of CFP. CFP4 is about half the size of CFP2. All right, a little bit about the CFP2 media module. This is the one that most vendors will be shipping this fall and starting early next year. So if you're interested in 100 gig, make sure to ask your vendors if they're supporting CFP2, because that'll give us a lot more density, as I mentioned. The cool thing about the CFP2 is it takes these internal components called the gearbox, which does signal conversion between 4 to 10 or 10 to 4, or whatever signaling you have on your ASICs. This component is currently in the CFP module. So we're taking that out, actually putting it on the board with the PHY or the Mac or whatever ASICs are on there. So that makes the module smaller, and it also allows it to support a lot more interfaces because we have 2 speeds that can run into the CFP2. So it can support 10 gig and 25 gig lanes. That allows us to support all the existing Ethernet standards that we have in the CFP in a much smaller and cheaper form factor. Okay, so what's going on in the IEEE? There's a couple interesting projects. The first one is the Copper Cable Task Force that is going to have a standard in March 2014, assuming they're on schedule. This one is probably not so interesting for us as network operators, but it's interesting because they're defining a copper backplane Ethernet standard. This is more interesting to the server vendors. So if you buy a lot of servers, I think you should talk to your server vendor about what they're doing with backplane Ethernet. It's interesting, some of the things that have been proposed is that they want to use actually an Ethernet backplane to interconnect a bunch of servers in a chassis or something like that. And it actually makes sense if we're going to have 100 gig in servers. I think it was projected that we'd have servers with 100 gig in about 2017 to 2019 sometime time frame. So it makes a lot of sense to have a 100 gig Ethernet backplane in a server that then drives a 100 gig Ethernet NIC on a server. So it's cool technology, I think. And then what's more relevant really to this audience is that we have some shorter reach interfaces that the IEEE is developing. So they're working on a 500 meter single mode interface, it's called NR4, and then a couple shorter reach multi-mode interfaces called UR4, and then a new signaling for SR4. These will run over probably OM4 multi-mode fiber, possibly OM3, so that's still to be determined. Now the other thing that I want to point out is that these are all parallel fibers. And you'll see this trend is that we have some constraints that we're working with. We can't, we have 19 inches of rack space to work with, so we can't make wider equipment. So we're really constrained on the front panel and the type of signaling that we can do. So one way to do more faster is to do things in parallel. So parallel is a big thing just for the short reaches, obviously. We can't do 10-kilometer parallel fibers or something like that. That wouldn't make sense. But in a data center where you typically control your own cabling, parallel fiber is probably an okay solution at a cost trade-off. So you have a parallel fiber, but it's going to be cheaper than integrating some sort of WDM component into the optic. Putting it all together, this is what first generation and second generation looks like. First generation CFPs, you can get about 4 ports on a line card. second generation CFP2. You can get about 8 ports on a line card. It's less expensive, less power, and as I said, it's going to be on the market at the end of this year, and then starting next year too. We'll see a lot of CFP2 line cards on the market. And then lastly, here's my horribly dense table, but I try and put everything on one slide, so if you've seen this table before, I apologize. If you can't read it, I apologize, but just remember that this table is in the slide deck, that you can use it as a reference, and that it has almost everything you would ever want to know about 100 gig Ethernet in one handy location. Okay, so on to what's beyond 100 gig. So I love this saying. It says, all solutions are good, fast, or cheap. Pick any two. You know, that goes for network design. It also goes for optics and standard design. What the IEEE does is really to provide a forum where everyone can come together and talk about all the solutions that are available. The IEEE has to make this balance cost that takes into account all the technical things, so the form factor, the optical signaling, the electrical signaling, all the things that make it technically feasible with the market requirements. And remember, the IEEE is trying to satisfy a bunch of different markets. So data center operators probably have different market requirements than an internet exchange or a broadband provider or a service provider that has a European-wide backbone. So we have to satisfy all these different markets with one solution. So again, cost and economics really dictate what we can do. So that brings us to what's next. If you look at the requirements projection, the IEEE did this back in 2007, but I think the graph is still accurate, and if you kind of extend the red line beyond where it was then, you can see that we're going to need terabit link capacities soon. That means terabit link capacities, not necessarily a terabit Ethernet. So we can do that with lag, we can do it with 100 gig lag, you know, we can do it with some sort of faster technology, but the point is that we do need something faster in the next couple years, as some service providers already are pushing the limits on 100 gig, and they'll definitely need a faster capacity. So the next speed is going to be 400 gig, and why not terabit Ethernet? So terabit Ethernet is basically technically and economically impractical to develop. So back to that scale thing, if we build something, there has to be a market for it. So if we build terabit Ethernet and no one can afford it, then that doesn't really work. Or if we build something really, really good and cheap, but it fails all the time, so it's not really that good. It looks good on paper, but then you deploy it, and you know, we have all these errors, and that doesn't work either. So we really have to find that balance between what's economically feasible, what's technically feasible to develop, because you know, we have to have a market for it in the end. So the choices are basically, okay, we had 100 gig in 2010, so we can wait maybe until 2020, 2022, until we can actually build terabit Ethernet, meaning there would be nothing in between 100 gig and terabit Ethernet for maybe 8 years. So that's kind of, or 12 years, that's kind of a long time. We had 8 years between 10 gig and 100 gig, and some people felt that that was too long a time. Or we can start something now that we know will work and will be ready sort of mid-2000s, 2016, when the market actually will need higher speeds. So those are the choices we had. Given that we didn't want to wait, the only choice really was to do 400 gig Ethernet, and that's how we came to that conclusion. There were two IEEE study groups called the BWA and the HOC. They basically did a lot of research into the market on technical solutions, market demand, and things like that, and they came out with a clear degree of consensus that 400 gig should be the next speed. You can see this by the votes that the IEEE did in March, is that there were no no's and mostly yeses. So that's good, because when we did .3BA, which was 40 and 100 gig, we went into the study group being called the higher speed study group. So we knew that we needed a higher speed. We didn't know what it was going to be, and then the IEEE spent a lot of time analyzing the market and figuring out what we need in different technical options, and we decided on 100 gig, and then some people came and said you need to do 40 gig too, and we came out with 2 standards. So 400 gig will go faster because we're already going into the standards process with a clear speed objective. So that will really help us. So this is why terabit Ethernet is really impractical today. Patrick, this is to answer your question. So yes, we could build a terabit Ethernet module. Yes, we could do it with 40 channels of 25 gig. Yes, it would be a gigantic module. That's an engineering term that my engineers told me. They said we could build a module and it would be gigantic. And I said, okay, well, how gigantic? And they said, basically, it all comes down to power and cooling. So we can cool about 2 watts per square inch. If we make some extrapolations, we could say, okay, we'll probably need between 100 and 120 watts of power. So that means the module itself is about 60 square inches. So that takes up over a quarter of a router board with just the module. Right? And that's just assuming that we could fit it on the board, not even talking about can we get the signal integrity right, can we even get 40 channels into that form factor, can we cool the module. That's just saying, you know, okay, estimate would be really big. So that's just really impractical. So where's 400 gig going? The CFI was presented at the March IEEE meeting last month, on March 23rd, I believe. I'm sorry, March 22nd. So it was passed. It's now an official study group. The study group is going to define the objectives. Speed is already decided at 400 gig, as I mentioned. And we expect to have a standard in 2016. You can go to the web page at this URL, and there's already an MSA. MSA is multi-sourcing agreement. It just means that a bunch of people get together and say, we're going to build this module, and this is what it's going to look like. So it's happened for every optics form factor out there. So there's an XFP MSA, there's a CFP MSA, there's a SFF MSA, so all different standards group. This is what we estimate for 400 gig is over the generations that we would expect, first, second, and third generation. The first generation would just be a very large module, possibly larger than the CFP today. It's also an interesting option that people are talking about, which is trying to use 400 gig CFPs to do 400 gig, and then this single mode cable that you see there is a multi-fiber cable. So you would have some sort of aggregation of 4 100 gig modules that then would do 400 gig. Interesting option. It's trying to compare basically the costs of 4 CFP4 modules versus 1 CDFP. So we'll see how that works out in practice. And then over the next generations, as we get faster electrical signaling, we'd have the second generation and then third generation. In the third generation, you'll see that we're actually doing 100 gig serial signaling. So this aligns with that, the second slide where we had the bell curve, right? And we had 100 gig serial. And then you can also see that this is where Terabit Ethernet becomes possible. Because if we have 100 gig serial signaling, then it actually does make sense to do 10 times 100 signaling to get us up to a terabit. So there's already a couple of different designs for a CDFP module, and as I mentioned, we're kind of have this trend going to multi-fiber cables for short distances. So one module that's proposed could actually use 32 fibers, so 16 transmit and 16 receive fibers, so a high density 32 fiber single mode cable. And what that gives us is some really awesome density. So if you put this all together, we could have potentially in a 1U or a 1 blade, we could have up to almost 4 terabits of front panel capacity. So that's really a lot higher density than we have today if you consider that we have 400 gigs or maybe 480 gigs if you're using 10 gigs. So that's a lot higher capacity. And then they're talking about trying to combine these ports into a higher density connector using 2 of them to actually give you 800 gigs capacity, you know, in one small optics module. So we'll see how that works out in practice, but these are some of the ideas that are being kicked around for the CDFP. If you want more information, there's all these links that you can go to. All the IEEE material is public reference, so you don't need a password or anything to read up on any of these things. The one that I would point you out is the one on the one at the end. That's the call for interest presentation. That's the one that was given in the IEEE last March or this March that started the study group. So it has a lot of the background information and a lot of the data that some of you actually contributed into the IEEE study groups. So, summary of where we are, talking about 10 gig to terabit. 10 gig is widely deployed. It's driving the need for 40 gig. We'll see, if we don't have on the market already, we'll see servers with 40 gig LOM or LAN on motherboard already on the market, coming on the market soon. Probably need 100 gig by 2017, 18, maybe 2020 on servers. 40 gig is pretty mature technology. I didn't really talk about 40 gig, but it's mature technology. We'll probably have smaller form factors like an SFP Plus type form factor in the near future. 100 gig, like I said, is still a couple of generations away from 100 gig serial, but we're working on 4x25, and we'll try and do 2 times 50, and then we'll do 1 times 100. It's getting really hard to make the electrical interfaces go faster. 400 gig is just starting. It's going to reuse 100 gig components, and then terabit Ethernet for now is really still science fiction projects, but give us some time, and it'll become feasible. And that was the last slide. So questions, comments? Usually this is where Randy Bush yells at me.
Tom Bird from Portfast. How do you balance the packets across the 10x10 or 4x25?
Good question. Let me flip back to this real quick. The answer is that it's bit striped. So it's bit striped at the bit level. It's just striped over all these lanes. So the packet or the frame doesn't know that it's being broken up and striped over all these lanes.
How do you deal with diffraction?
Diffraction is actually done in the individual optic. So there's, right, you see there's a DWM mux and then a DMux. So that takes care of all the, the fiber and signal integrity on the optical side. So it keeps constant measurements, and it has like a little bit of buffer. So I mean, ideally, it's going over the same fiber. So you shouldn't have like really diverse latencies, but certainly there could be some variation in latency, or maybe one fiber is bent a little differently that causes some diffraction or something. So, but it's all at the MAC level, so the MAC and PHY level. So your Ethernet driver sends a packet, the MAC splits it up, and then it comes out an Ethernet packet on the other side.
Thanks, Greg.
Simon Kelly. You concentrated a lot on the problems of building these modules, basically the stuff at either end of the fiber, and you didn't really talk about the switches that are connecting them together. Is that because the switches are relatively easy, or is that just a whole different problem?
No, that's a whole different part. In fact, I gave a presentation at the last RIPE in Ljubljana about how there's basically, well, I'll sum it up in a nutshell, but basically we need 2 components, ASICs and memory. So for 100 gig, we have a packet coming in every, does anyone know? Anyone remember? It's every 6.72 nanoseconds for 100 gig line rate at 64 byte frames. So the memory cycles that we have today are on the order of 10 nanoseconds. So for now, we have to do packet lookups in parallel, and we have to use like really clever kind of memory tricks in order to be able to look up a packet and not drop it on the floor. So yes, and that's another good point, and that's why I have on this slide, it's front panel capacity, as in how many optics can we line up and put on a panel, not can we actually send this much data through a blade. But yeah, so generally speaking, the ASIC technology that we have is still following Moore's law, so we're seeing commercial deployments of 22 nanometer and 30 nanometer technology, and then the CAM and SRAM memory roadmaps that we have are keeping up with the packet lookups that we need to do. But good question. I'll be happy to, I'll talk as long as you want over beers.
Just one question from me. Sorry, I wonder if you guys. I'm at a company in Israel called Compass EOS. I don't know if you've heard of them. They've got a really impressive, true photonic integrated ASIC. I wonder if you guys are looking at that and if it's on your roadmap.
So that's definitely so. What Neil's talking about, right? Neil or Patrick?
Neil.
Neil.
Neil's the good-looking one.
What he's talking about is there's some technology that basically, right now we have the ASIC and then the optic is a separate component. So there's technology coming on the market by several different vendors that kind of merges those two into one, and it combines them and makes them a lot more efficient. So personally, Brocade is not involved in that effort, but there are definitely companies like the one that you mentioned. Lightwave that Cisco bought was kind of one of those companies that was doing those things. But it's a definite trend on the market, and we should have a presentation at the NANOG in New Orleans by Finisar, who will talk about like everything that's going on in the optics market. So I hope that comes through. But that's a good question. That's a whole another discussion that's definitely interesting. So that's why we're trying to get it on the agenda for NANOG. Yeah. Okay, I guess no more questions?
Okay, thank you, Greg.
All right, thanks, folks.